Imagine this. You're trapped 30 miles from the nearest way out, and you've got the weight of an entire ocean pressing down on you. I mean, this isn't some sci-fi movie. This was the actual challenge of building the Channel Tunnel. You know, when Napoleon first saw plans for one way back in 1802, the tech to fight the laws of physics that deep it didn't exist. So today, we're going to dive into the invisible forces that engineers had to conquer, and this is the cool part, how a forgotten invention by Nikola Tesla might just be the key to the next great frontier, a tunnel all the way across the Atlantic.
So, what do you think is the biggest threat down there? The crushing water pressure? A catastrophic collapse? Yeah, I mean, those are definitely huge, terrifying risks. But the most relentless enemy engineers had to defeat, the one they were constantly fighting, was something else entirely. Yep, the air. Believe it or not, the very air the train is moving through becomes this massive, invisible wall. And figuring out how to get around that wall is the first big secret to conquering the deep.
Okay, let's get right into this because it's the fundamental challenge for pretty much any high-speed tunnel. They call it the piston problem, and it's a force of nature that had to be tamed with some serious engineering muscle.
Just picture it. A train blasting through a tunnel is basically a piston inside a giant cylinder. It's not just slicing through the air, it's pushing a colossal column of it forward. This compresses the air into a wall of resistance so powerful it would actually make high-speed travel impossible. It could even damage the tunnel itself.
So how'd they solve it? Well, the Channel Tunnel's solution was an incredible bit of brute force engineering. They built 194 of these things. Piston relief ducts. They're basically just vents, but they're strategically placed to let that compressed wall of air escape into the other tunnel, which relieves all that pressure. It's a really smart but very active solution. All right, so to build those tunnels in the first place, you need some truly wild machines. They didn't just dig a hole. No, they sent 11 gigantic robotic caterpillars to crawl under the sea. These are tunnel boring machines, or TBMs. And the truly amazing thing is how they work. They do three things all at once. A massive cutter head grinds up the rock at the front. A screw conveyor pulls all that debris, they call it muck, out from the front. And as it inches forward, the machine is simultaneously installing these precast concrete rings to build the tunnel lining. It digs, builds its own support, and then literally pushes off the ring it just built to move forward, exactly like a caterpillar. And this right here just highlights the sheer scale and finality of this project. These multi-million-dollar machines only go one way, forward. For some of them, it was actually cheaper to just drive them off into a side tunnel and entomb them forever than it was to even try and bring them back. A one-way trip. But before these giants could even get started, the prep work was just immense. They had to find the perfect geological layer, this stuff called chalk marl, which is a kind of clay that's stable and waterproof enough to work in. They also had to dodge these dangerous fissures that, under the incredible pressure of the sea above, could cause a total collapse. To do that, they actually drilled probe holes 250 meters ahead and injected the earth with a stabilizing grout. And critically, they drilled the smaller service tunnel first just to get a live preview of the geology they were about to face. Now for the part that just seems impossible. How in the world do you get a machine starting in England and another one starting in France to meet perfectly in the middle of the English Channel, deep under the seabed, with absolutely no GPS? You know, up here on the surface, we take precise location for granted. But deep underground, GPS is totally useless. You're flying blind. You have to somehow transfer coordinates from the surface way down into the earth with absolute pinpoint precision, using techniques that are both ancient and incredibly clever. The answer is this brilliant technique called shaft plumbing. Essentially, surveyors use an instrument that can look perfectly straight up or down. They use it to drop a laser down a shaft to set up a known coordinate point deep underground. From that point, a laser mounted in the tunnel guided the TBM by hitting a photosensitive target on its frame. If that machine drifted by even a millimeter, a computer would scream a warning at the driver. And the accuracy they achieved? It's just staggering. On October 30th, 1990, after burrowing for miles from opposite ends of the channel, they stopped the main TBMs and drilled a small probe hole. It was just 5 centimeters wide, and it broke through exactly where it was supposed to. That tiny hole was the signal, the confirmation that miles and miles of careful calculation had actually paid off. A little over a month later, on December 1st, British and French workers met face-to-face, creating the very first land link between Britain and mainland Europe since the last ice age. A truly historic moment,
all made possible by lasers and physics. So, the Channel Tunnel solved its physics problems with these massive, active systems that are always working, always fighting against nature. But what if there's a more elegant way, a more passive way to control these huge forces? This is where we pivot from the past to the future, with a forgotten invention from the brilliant mind of Nikola Tesla. Tesla designed this, the valvular conduit. It's a one-way valve, but here's the totally mind-bending part. It has 0 moving parts. It's just a single, solid piece. The magic isn't in some mechanism. It's baked right into the shape itself. So how on earth does it work? Well, in the forward direction, the fluid, or air in our case, flows through in a nearly straight, super easy path. But when you try to push it through in reverse, the geometry forces the flow to diverge, to split up into all these different streams, and to basically fight itself, losing energy and momentum with every single turn. Let's just walk through that. In reverse, the flow is forced to split. Part of it slams into these bucket-like structures, which just kills its momentum. Then the flow has to make a sharp 180-degree turn before it collides with the main stream of air coming in. This whole chain reaction of collisions and turbulence creates massive resistance, and it effectively stops the flow without a single moving part. Okay, let's connect these two incredible stories. The Channel Tunnel is a masterpiece of engineering that uses machines to fight physics. But Tesla's valve, that points to a future of what we can call fluid logic, where the structure itself does all the work. You have to remember, the Channel Tunnel needs constant, active engineering to function. There are 50 kilometers of pipes circulating chilled water 24/7 just to fight the heat generated by air friction. And massive fans are always running to keep the service tunnel at a higher pressure so that if there's a fire, smoke is literally pushed away from the escape routes. It's all active, all mechanical, all the time. This slide really just lays out the whole paradigm shift. The channel uses mechanical vents to fight air pressure. A future tunnel could use passive geometry. The channel uses high-pressure fans for safety. A future tunnel could have self-regulating airflow. The core idea completely flips, from using machines to fight physics to designing things so that physics does all the work for us. So what we're really seeing is this incredible transition. We're moving from an era defined by powerful machines and raw power into a new era of fluid logic, where the intelligence is literally baked directly into the shape of the things we build. Which, of course, brings us to the final, fascinating question. The challenges of a transatlantic tunnel are orders of magnitude greater than the channel. I mean, they're almost unimaginable. Mechanical, brute force engineering might not even be enough to get it done. But if we can truly master this idea of fluid logic, are we maybe one step closer to making that audacious dream a reality?